Hello everyone. My final project is called Predicting Antibody-Inducing Activity in COVID-19 B-cell epitopes using machine learning models. In this project, we are working with COVID-19 cell epitope prediction dataset, which has been obtained from IEDB and UniProt and is available on Kaggle. The dataset consists of 40,807 rows and 14 variables, including protein and peptide features, as well as the target variable antibody valence. Our primary task is to perform binary classification to predict whether a given amino acid peptide exhibits antibody-inducing activity, with the target variable being either positive equal to 1 or negative equal to 0. The primary business problem we are addressing in this project is to predict whether an amino acid peptide exhibits antibody-inducing activity. Our objective is to develop a machine learning model capable of accurately predicting the antibody valence of peptides, which can have a significant impact on vaccine design and development, and thus combating COVID-19 in the future. So I started first by loading and exploring the data. I will explain this looking at my code. So first, I downloaded 3 different datasets that relate to the antibody response: input bell.csv that contains the related B cell in vitro, and input sars.csv containing the data of SARS-CoV-1. They were combined in one set to use for my classification task, and a third dataset also that consists on unlabeled data to predict. So the data set that I combined contains now 14 variables and 11 continuous 11 continuous ones and 3 categorical variables. The categorical variables, including parent protein ID, protein sequencing, and peptide sequencing, were removed because they were not needed for the model, since they already computed the physical-chemical properties that I'm using as predictors. I created a new variable to represent the length of the peptide calculated at the difference between an end position and start. I used summary data to look at the basic statistics, and that showed some variables had wide range of values while others have smaller range. I completed by the pairs.panel that showed the distribution, like histograms that showed that some variables had a skewed distribution, while other ones like Shu, Fassman, Kolaskar, Tongakar, and Parker had a bell-shaped distribution suggesting normality, while the other one were skewed. So I decided to complete by a normality test under certain Darling test on each variable. The p-values obtained for each variable were extremely small, indicating a strong evidence against the null hypothesis that the variable follows a normal distribution. Therefore, I conclude that these variables are not normally distributed. I then looked at missing values. There were no missing values in my data. I also looked for outliers using a box plot at first. Looking like there's a lot of outliers. I also used the IQER method, finding that there is a significant numbers of outliers in this data set, and the data, since it's non-normally distributed, instead of imputing these outliers with the median, I've decided to leave them as they are, as they may have a meaningful impact on the prediction, normalizing the data afterwards. To explore the correlation, I created a heat map and a correlation matrix to analyze the relationship between the predictors and the dataset using ggplot2. So these two did not show strong evidence of multicollinearity, except for start position and end position, which had a correlation coefficient of 0.99, indicating a high correlation. The highest correlation for the rest of the predictors was 0.69, which is not very high. The heat map also revealed that the most of the features, except Shu Fassman, have weak correlation with the target variable. This can suggest that the feature may not be strong predictors. So I used table and bar plot to explore the response variable, and it's shown that it was imbalanced in favor of the negative class, 72%, and 27% in favor of the positive class, which is antibody valency. Finally, the data transformation that was done to prepare my data for the models was creating a new variable called peptide length. I normalized also the data using the min-max scalar method with a range of -1 to 1. As you can see in the code, this was done after splitting the data to train, test, and validation, and the normalization happened with the min and max of train to avoid information leakage. Noting that I did apply PCA to my code, but I did not feel the need to use it since I have only 11 variables and not really a big high dimensionality, and also not high multicollinearity. I also at one point transformed my peptide length variable to a categorical variable, small, medium, and large, and then dummy coded for the models. But when I tried it, it did decrease the performance, so I'm not gonna use it for applying my models. So now let's talk about the models I used to train my data. I chose to use logistic regression, SVM with radial kernel and random forest. I trained it to predict my binary target variable. The evaluation metrics used are accuracy, precision, recall, F1 score, and area under the ROC curve. I also used some improvement techniques that I'm going to show you in my code to improve the overall performance of this model. So let's start with the logistic regression model. So I applied a GLM function with default parameters to my data. The logistic regression model performance appeared to be, when evaluating, appeared to be suboptimal with an accuracy of 74%, a low kappa with a low precision, and with low kappa would be a slight agreement between the predicted and actual classification beyond what would be expected by chance. This suggests that the model overall performance is not very satisfying. In order to improve the model's performance, I applied the technique of AIC stepwise selection, as seen here, but with no no improvement here. So I decided to complete then with an hyperparameter tuning with 5-fold cross-validation using the caret package to further enhance the model performance. The tuning involved parameters as alpha and lambda, which correspond to L1 and L2 regularization, and used the glmnet method. So as a result, there was a slight improvement, but the kappa remained low, indicating that the overall agreement between the predicted and actual classification still has room for improvement. Also, the area under the curve was 0.64, indicating the logistic regression model doesn't really have an ability to discriminate between positive and negative cases. So for the SVM model, initially an SVM model with a radial kernel was built with default parameters and exhibited a moderate accuracy of 77%, but its performance in terms of recall and F1 score was relatively low, with 0.2 recall and 0.2 kappa also, which suggests there is room for improvement. So in trying to improve it, I did a hyperparameter tuning with 3-fold cross-validation. So when evaluating the tuned SVM model, it demonstrated a slight improvement in accuracy, precision, and F1 score, while the kappa value remained relatively stable. It indicates that the hyperparametric tuning using cross-validation had a positive impact on the model's performance, and we're gonna use this model as the best model. Now let's talk about the random forest model. The initial performance evaluation of a random forest model applied with default parameters. So the initial model showed satisfactory performance metrics with 87% accuracy, 0.7 recall, a kappa of 0.66, also a precision of 0.78. But to improve this model, I decided to complete with the weighted model, since my data is imbalanced. So I attributed class weights to the data, with 1 for negative and 4 for the positive one, which is the minority one. When performing the evaluation, the metrics did not change that much and kind of stayed the same: accuracy and precision and recall. But the OOB estimate of error was 13% compared to 12% for the initial one. The decision was to stick with the initial random forest model. So as we can see from all the evaluation metrics of the models, the best model for this data was a random forest model. Now we're gonna complete with the ensemble function. So as you can see, to build an ensemble model, an ensemble function was created. This function takes the logistic regression, the best one, the SVM and random forest models, along with the new data as an input. It then obtains the predicted classes for each model using the corresponding prediction method. The predicted classes from the individual models are combined into a matrix where each row corresponds to an observation in the new data. Next, the function computes the mode, the most common value for each row of the matrix. The mode represents the ensemble final prediction for each observation, which is based on the majority vote of the individual models. So this function returns the combined prediction for all observation. So then I proceeded to compare the individual models with the ensemble model evaluation on my test data, not validation data, and proceeded to do the metrics as usual, the different metrics for each model. So looking at those metrics: accuracy, precision, recall, F1 score, and area under the curve, I've seen and concluded that the random forest model outperformed the other models in terms of accuracy, recall, and F1 score. The ensemble model and random forest model had the same area under the curve, which was the highest amongst all the models. Precision was high for random forest model, and precision is really critical in vaccine development and very important in this field. Therefore, I chose the random forest model to be the most suitable choice for predicting antibody valence in the context of vaccine development. For the rest of the project, and as asked in the project, I proceeded to predict the target labels for the unlabeled data that I have, which is the COVID test, and I also did a bagging for the random forest model. So I trained the random forest on 10 samples. Then I calculated the prediction and combined those predictions using majority vote. Then constructed my confusion matrix to see, and comparing the two models, there's an improvement using the bagging random forest model. Also, it makes it more robust and less prone to overfitting. In summary, we developed and evaluated classification models to predict antibody valence in vaccine development. We used logistic regression, SVM, and random forest models, along with data transformation and performance improvement techniques. Improvement techniques like hyperparameter tuning with k-cross-fold validation and class weight balancing, also AIC stepwise. An ensemble model was used, built to improve the performance, also evaluated with various metrics. The random forest model was identified as the best performing model based on comprehensive performance metrics, especially the precision in this case. Key lessons from this project. Data transformation and performance improvement are crucial in developing accurate classification model. Ensemble models can improve overall predictive accuracy, but individual models can still outperform the ensemble model. Precision is crucial in vaccine development, as false positive prediction can result in harmful vaccines. In the presence of the imbalanced data, accuracy can be biased, so highlighting the importance of precision, recall, and area under the ROC curve is critical for the best performing model. And finally, key limitations and future work. So the limitation would be the presence of outliers and class imbalance in the dataset, despite data normalization, limited dataset size, and weak correlation between features and target variable, potential for overfitting in complex models. For future work, incorporate additional relevant features and explore advanced feature engineering techniques, experiment with other machine learning algorithms, ensemble methods, and techniques for addressing class imbalance. Also, we can try to optimize hyperparameter tuning and cross-validation and evaluate the model on new and seen data. That's it. Thank you very much for your attention.